So hello everyone and welcome to this next lecture in the DC to DC video series. And in the previous lecture I had stopped here where I was building the model for a transformer. So in this lecture I will continue with this transformer model and write the actual equations rather than just the basic model. So as before I start the actual lecture, a little bit of background that if you are interested in these kind of video lectures but you want something a little more comprehensive, I do have a full-length course on simulating power electronic circuits using Python, and that is available on this MOOC website Udemy. In this course, I talk about the entire basics of how to install Python, how to install Python power electronics, a little bit of basics of electrical engineering and power electronics, and finally a case study of how to simulate a buck converter. And there is also, if you're interested more on the digital programming side, digital signal processing side, or the control side, I have another course on the basics of digital signal processing for power engineers. And in this course, I talk about how you can design and implement a filter using Python. So there is a bit of basics of signal processing, and also there is a case study on how we can design and implement a notch filter and a low pass filter using frequency response characteristics with Bode plots using Python. And finally, and this is what is most relevant for this few lectures, is the simulation of magnetics for power electronics using Python. And in this course, I talk about how you can simulate magnetic components like inductors, coupled inductors, and transformers for power electronic applications. And it finally concludes with a case study of a flyback converter. Right? So the flyback converter has a multi-winding high frequency transformer. So this case study is most appropriate for, or rather this course is most appropriate for the simulations that we are undertaking in these next few video lectures, where we will simulate a transformer and later simulate converters using transformers. So going back to our video. Now let's go back and see, this is where we had left off. Now this is where I had written the equations for the model of a transformer. In this lecture, let us actually start plugging in these values. So to begin with, if I go back to the simulator page, I still have not added the circuit file. So for that, let me go back and check that this is a two-winding transformer. Okay? This is what we had created in the previous course. This is the model for a transformer where I assume each winding to be a controllable voltage source in series with a variable resistor. Right? And we are measuring the voltage across this controllable voltage source, so this becomes the winding voltage, and this is the case for any winding which is present. We start with a two-winding transformer, but we could easily expand this to several windings, as we will do in the later lectures. So first and foremost, we will need to add this file. So let me go over to the simulations, basic converter, and here there is a two-winding transformer. So I'll just call this transformer, save the file. Now if you notice, this is just the model of a transformer, right? It is energized with these two terminals, and it could be either energized with these two terminals as well, or it could be supplying a load, right? So basically there is an energy source on one side and or an energy source on the other side, or just a load, right? So as you all know, a transformer can have any different combinations, and we could see that in the next few lectures. So in order to make this useful, or rather to complete the simulation, I will add a source on one side. So let me go actually create another Excel sheet, and here I will create a voltage source. So as before, I'll just put out the skeleton. And just put a voltage measurement. So this will be a voltage source, and we can call it as SRC. You can think of a better name if you want. And as before, I will give it a parasitic resistance, and I'll put an ammeter as well. Now here I shall measure the voltage of this source. Now it is important to understand that in any electrical circuit, you will have multiple measurements. For example, we are measuring the voltmeter across a winding. Right? Now, you could argue if you're measuring the voltage across the winding, why measure it again? But in almost every circuit, you will notice that some measurements are done additionally. So there are redundant measurements, right? And it is always best that even if you're measuring a quantity, it might be best to encapsulate one particular component and measure it again for other purposes, right? So coming back here, this is the voltage. Now I need to add the terminals. This source, let us say, is being energizing the primary or winding 1. So coming to this is the transformer. This is winding 1 of the transformer. Right? This is winding 1. These are the winding 1 terminals. So what I would say is, it is a safe option if we select these terminals and paste it in this where we are supplying the other one. Right? So this voltage source is now supplying winding 1. So let's save this file and we go into energy series, simulations, basic transformer. As before, in the formats, I just choose text.csv and I'll call this volt source. Right? And I can say OK to these values, no problem. So with this done, we have now taken care of the primary winding. So the primary winding is being energized by this source. Now the question is, what happens to the secondary winding? The secondary winding has to do something. We have to close this loop, right? It's important to note that no branch can be left broken. So we need to create another Excel sheet. And here again, let me just quickly create a skeleton. Let's just connect a load. So here let me connect a resistor load. Let me put an inductor. And let me put an ammeter. And here let me connect a voltmeter. Now these two will have to go. And we will pick out these two terminals from the two winding transformer. So these terminals, these are the terminals of winding 2. These terminals will be connected to the load. So therefore winding 2 is now supplying the load. So let me just copy this. Go to this untitled and let me just paste it here. Okay, so this needs to be adjusted. And this should complete our circuit. So let me save this. Again, I go to energy series, simulations, basic transformer. Always make sure that all your files are in the same working directory. And let me call this secondary load. Right. So let me add these two files as well. So choose the file. The first one will be voltage source. And let me call this source. Save it. And then choose the load. So this is the secondary load. And I will call this load. Save the file. So with this, we can process the circuit schematics because we've completed the loop. And as you can see, the circuits do not have any detectable errors. So we are good to go. So now that we have the basic circuit, the next step is we can start plugging in these values into our control code. So the first thing we need to do, of course, is edit circuit parameters. Right? Now, let us look at some of the parameters here. Many of them can be left as it is, right? So let us first start with a 240 by 240 volt transformer. So we have 240 volts in the primary, 240 volts on the secondary. This is just to start with. We can think of better solutions much later, but for now let's start with something very simple. So the ammeter load should be downwards. This ammeter load should be downwards, so let's just change that. This should be 5F because it is now 4F. The inductor and the resistor. Now you can choose anything you want because this is just a load. So what I would say is we can leave it as it is for now. Since we have a 240 volts in the primary and the secondary, the voltmeter should be much higher as a voltage level. So let's just change this. So I'll make this 1000 volts. The positive polarity is 7C, which is perfectly okay because it means the positive polarity of the voltmeter is towards the upward direction. So we just save it. Go back to the circuit list. This is a transformer model. Now, the ammeter. The first thing is let's go over to our ammeter circuit. So, the ammeter is these two ammeters. Let's go have a look at it again, which is it. Ammeter winding 1, transformer 1, right? That is this one. Now, in terms of a model, there are various directions that we can take. So we can choose this because remember this is our own model. So we can choose any direction we want. In all my simulations, whenever I simulate a magnetic component, I will always assume the current flowing into this magnetic component. So it is always flowing into the winding, which means the direction of current, positive direction, should be downwards, and the same goes for this as well. So I will just edit this and make it 4G, and the same goes here. I'll make this 4I. Now the control voltage source. The control voltage source is this one. The positive polarity of this control voltage source is upwards, right? Because this is the winding voltage which we want to appear upwards. It can be downwards also, but it's always, if we are supplying a voltage such that the positive terminal is upwards, this control voltage source will also have a direction which is where the positive polarity is upwards, and the same goes for this. So both of these can have positive polarity upwards, right? And that is the case, so we don't have to change it. The control name can be given any unique name. It's not really necessary. This is more for debugging purposes, which can come later, but for now we can just maintain this to be the same as the component name. So I will just copy winding 1, transformer 1. The initial voltage can be 0, positive polarity is 5G. That's perfectly okay. So the next is we come down here, and for this all we have to do is copy this, the name of the component, winding 2, transformer 1. The positive polarity is 5I, component position is 6I, which is perfectly okay, which means the positive polarity is upwards. And continuing, now the variable resistor can be, this initial value is perfectly okay. All we have to do is just change this control name. So let me copy the name of the component. And the same goes here. Actually, there's a typo here. This should be winding 1 and winding 2, but anyway, it doesn't matter. I don't want to change it now. Now, voltage 1, this polarity is perfectly, that is voltmeter. The polarity is okay because the positive polarity is upwards with respect to the component. It is only the voltage level that needs to be changed. So I'll just make this also 1000. And the same for the last one. It can be just 1000. So with this we are done with the transformer. Actually I still haven't finished. There's the voltage source. So the voltage source, the ammeter, let's go over to the voltage source. This is the voltage source. The ammeter, this voltage source will be supplying a current. So the positive direction of the ammeter is upwards, and that is the case, so we can leave it as it is. The resistance of the source, this is just a parasitic resistance. 100 ohms is way too large, so we decrease this. We can make this 0.01. And the voltage source we said we will choose a 240 volt RMS voltage. So 240 volt RMS voltage can be said to be something like 311 volts peak, right? And let's choose a 50 hertz supply. Since I am in Germany, I am choosing these values. If you are in North America, you can choose something corresponding to North America. For example, in North America, the voltage is 120 volts RMS, which corresponds to around 170 volt peak, and it is a 60 hertz voltage, right? So you can just make these changes if you are living there. The component position is 9A, positive polarity is 8A, so this can be as it is. Now, the last is the voltmeter. This is pretty simple. The polarity can remain as it is. The positive polarity is 7C, component position is 8C, so which means the polarity is upwards. It is only the rating that needs to be changed, so let's make this 1000. And with this we are done, right? So we can go back, and now we can go into control. So we've already started editing this control file. Of course, we've not put anything sensible into it, but that's okay. Let's start adding. First we can just add this control file. So it's a transformer model.py. So let's call this transformer model and save it. So the first thing is, let's start configuring it. Now this transformer model, as we already said, it is a model with inputs and outputs, right? So each winding has inputs and it has an output. The input is this applied voltage, and that applied voltage is measured by this voltmeter, right? At the same time, this control voltage source is the output, and so of course is also this variable resistor. So these two are the outputs. So let's configure them. Let's go over to the web browser and let's add a control input. So the control input is, as we already said, the 2 voltmeters. So there is voltmeter winding 1. Let's call this V, or let's call this V winding 1. Alright, save the input. Actually, maybe I should put an underscore just to differentiate between the V and the winding 1. So we have this one, and add another one, and let me take this to be the voltmeter winding 2, right? Because remember, there are 2 windings. For each winding, the input will be the applied voltage, right? Now you might think that we are energizing only one, so how is the other one also the input? Well, remember, in a transformer, you do not know which side is being energized and which side just has a load, right? It is possible both sides of a transformer could be energized. It is possible any one side could be energized. So whichever side is being energized or whichever side is the load, the applied voltage, the voltage that appears across these terminals, is always the input, always. So let's call this V underscore winding 2. Save the input, and with this we are done. Now the control output, as I already said, the control output is this control voltage source and the variable resistor for each and every winding in this transformer. So let's add this control voltage, control output. It's already giving me this, so it's great. Control voltage source winding 1. So let's call this V source winding 1. Initial value can be 0. We're going to change this in control anyway, so we'll just save the output and add another control input, and this will be the other winding. So we will call this V source winding 2. Initial voltage can be 0. So the next is, well, actually I added a control input. Let's just go add a control output. these are the two resistors. So variable resistor winding, here I made a mistake, variable resistor winding 1, transformer 1. This is a typo, should have been G instead of W, but anyway. So I will call this resistor winding 1. Initial value can be just 100. Okay, you can't put a 0 for a resistor, don't do that. Give it some finite value. Save the output. And let's do this for the other one as well. So that is variable resistor winding 2. So I will call this res winding 2. Again, give it some non-zero value because a resistor should not be 0. Save the output. And with this, we are done with our inputs and outputs. Let's go and see how that works. So the first thing is this voltage V1, right? We know that this V1 is this measured voltage, that is the input voltage, right? So let's copy this and let's place it in the control file. This is our voltage 1, right? So we know that this is equal to E1 minus I1 into R1, right? Never mind for now what these values are, but what is important from this is that we now can write E1 as V winding 1 plus I1 into R1. Now the first thing we need to do is, before we finalize this equation, we need to figure out what is the direction that we are actually looking at. Now let's go and have a look. If you look at this current, if we assume a current which is downwards, right? If you assume a current which is downwards, in that case, the applied voltage and the induced EMF will be connected by the relation voltage minus the resistor drop is equal to the induced EMF, right? That is very important. So really speaking, we got our equation wrong. Alright, so it is voltage, that is this one, the applied voltage minus this drop across this resistance is equal to induced EMF. So let us correct it here. This applied voltage is equal to this, let me copy this here, paste it, is equal to the induced EMF, right? So we don't have to do anything to calculate our induced EMF. Alright, this is just the KVL. I would say take a minute and think about the application. I am assuming always the current to be flowing into the winding, right? And if it is flowing into the winding and this induced EMF is such that the positive polarity is upwards, just do the KVL. This is what you get. The applied voltage minus the drop across this resistor is equal to the induced voltage, induced EMF, right? So let's get rid of this. This is one of our equations. So all we have to do is copy this, paste it here. This is the second equation, E2. Now the question you might ask is, what is this resistance R1? This resistance R1 is the winding resistance of your transformer. Now it's very important to understand this is not the same as this one. This variable resistance is the resistance of the model, right? This is the resistance, this is the external resistance that we are connecting to ensure that our current is what it is, right? Because this is a voltage input current output model that we are creating. So therefore this variable resistance should not be confused with this resistance. This is the winding resistance. So let's give it a value. So I would say resistance R1, winding resistance, and let me give it a value R1, let's say give it 0.10, right? It may be a bit on the larger side, but the reason is that this resistance can sometimes also include certain other parasitic effects of this winding, right? So this is our first equation. Now that we have our first equation, the next thing is, what about this induced EMF? This induced EMF and this current are internal variables to the model. Now, as I said, and this is a recommendation, if we are not defining something as a constant, always let us declare them as static variables. So I will go over and create a static variable. So the first static variable will be E1. Initial value is output 0. That's perfectly okay. And the next static variable is E2. Initial value can also be 0, no problem. And then we need the currents. So add a static variable. The current I1, save it. And the last one is I2. All these can be 0, no problem. So with this, we are done. Now, before of course I continue, it's very important to understand that we need, for a control variable, this is something which I should add right away. Every control while should have a time event variable. So let me add a time event variable, make it 0. So this is our time event, and let me put everything inside this time event. So if t clock is greater than or equal to t1, and let me expand t1, or let me update t1 dt, and all the way on top I can just define dt, and I will define dt to be the same as the integration time step. So these equations will now go within this time block, right? Because these are the actual model equations. So now that we have this, the next one is this integral, right? We are now going to integrate this. So what that means is psi I1, rather psi 1 plus equal to the integral of E1 dt. See, this by Faraday's law, we know that the induced EMF is directly proportional to the rate of change of flux linkages of the winding. This means that the rate of change of flux linkages of the winding is the integral of this induced EMF, and that's what we've calculated here. So we can just integrate our induced EMF, right? Psi 2 plus equal to E2 into dt. That's it. We are just integrating the induced EMF. So this is our flux linkages. Now that we've calculated the flux linkages, these are the two equations that we are looking at, right? That is, the flux linkage is equal to this one. The flux linkage of winding 1 is equal to the current multiplied by the self-inductance of winding 1 plus the current multiplied by the mutual inductance of this winding. So let me quickly paste these two. And let me just write psi I1, psi 2. So now the question is, we now have to define these two variables L1 and M12. Now L1 and M12, these are the self-inductance and the mutual inductance. Now in a transformer, it is important to understand that what is this self and mutual inductance. This self and mutual inductance of a transformer is the self-inductance of the winding, right? So what that means is this winding, let's go back to the circuit. This winding is what appears here as the magnetizing winding, right? This is equal to what is known as the magnetizing winding. The mutual inductance is the magnetism that is produced, or magnetic flux produced by the other magnetic or the other magnetizing inductance, right? So that's what this is. Think of the actual equivalent circuit that we all know of a transformer. So now, how do we define this inductance? Now this lecture is already getting a bit long, so I would like to break this lecture now because the next discussion will be a bit long. In the next discussion, we will talk about how we can define L1 and define L2 as well as define M12 and M21, right? So if you had any problems following up till here, feel free to either comment on this video or message me on social media or send me an email, whichever is your preference. But I will continue this transformer model in the next lecture. As I said, this transformer model would take a bit of time, at least to do some justice to it. So I would like to take maybe another one lecture or maybe even one more lecture after that to complete this. So I would only say please do be patient, and of course if you need details, you are most welcome to check out this course where this entire topic has been discussed in much greater detail, and that includes things like transformer theory and the entire setup of a transformer simulation. So this is a much more detailed discussion on transformers. What I'm doing here is much faster because this is just so that I can simulate converters which have transformers. So once again, I will end this lecture now. Thank you so much for watching and see you next week. Goodbye for now.